Welcome to this video on compound functions. This is the second part that looks at a slightly more complicated example and introduces the concept of indenting compound functions. This video is based on materials created by Professor Mark Cavazza of the University of Greenwich and is presented by me, Andy Wicks. So let's get into the theory. In the first video, we looked at the fact that tactics matter. Slowly is faster. And what we do is a little bit, get that working, and then add a little bit more and check that that works, and so on. So we keep adding a little bit at a time. We do not try to save time by doing two or more steps at once. In part one, we looked at converting centigrade to Fahrenheit. But this time we're going to be using the roots of quadratic equations. Now it doesn't matter whether you understand roots of quadratic equations, whether you remember the formula. All I'm asking is that you accept that the root of a quadratic equation can be found by this function. Now the first thing to notice here is that this equation isn't one equation, but two. That plus or minus means that we've got the minus b plus the rest and the minus b minus the rest. So this isn't really one equation, it's two. And just as before, what we're going to do is we're going to make an assumption that we work through, see whether that works, and then we can use the functions that we create in Scheme to solve other problems as well. So let's assume that y is equal to x squared plus x minus 6. Now if that's true, then a is 1, b is 1, and c is minus 6. In other words, the thing in front of the x squared is just 1, the thing in front of the x is just 1, and the other bit is minus 6. So with those little bits of armour in hand, we can go and fight the war on this equation. The first thing we're going to do is to look at the minus 4ac. Well, that is just multiplying minus 4 by 1 by minus 6. Minus times a minus, as I'm sure you'll remember, is a plus, so we get plus 24. Having got that minus 4ac done, we can then take that answer and add it to b squared, because we've already taken account of the minus sign with the minus 4. So how do we do that? Well, b squared minus 4ac is the same as b squared is 1 times 1 plus the 24 that we got in the previous step. So 1 plus 24 is 25. Now we can move on to the next bit. The next stage is to find the square root of what we got. So we got an answer of 25. The square root of 25 is 5. Now we're ready to move on to that complicating bit of the equation that turns it into two equations. What we're going to do is we're going to do the plus bit first. So we're going to do minus b plus the square root of b squared minus 4ac. Well, to get the minus b, we just multiply b by minus 1. So minus 1 times b plus the 5 that we got in the previous step. And what we get is minus 1 plus 5 gives us an answer of 4. And now it's on to the final step. What happens when we divide by 2a? Well, we know that the previous step gave us 4. So all that stuff on the top that we can now forget about is just 4. 2 times a, 2 times 1 is 2. So 4 divided by 2 is just 2. So what we're saying is that the first root of this equation is 2. But now we have to worry about what happens when we have that other equation, the one with a minus sign just after the minus b. Well, for that, we just need to swap that plus to a minus. And if we do, we can see that what we get is that minus 1 minus 5 divided by 2. So now we get minus 6 divided by 2, and that is minus 3. So we've looked at how we can break this problem down into separate stages. So let's go over to Scheme and see that working. Here we are in Scheme, and we're going to create a function called R1. R1 takes three parameters, A, B and C, the ones that we got when we were looking at working the problem through manually. And the first step was to find out what happened when we multiplied -4 by A and C. Now we can call that function using R1, 1, 1 minus 6. And if we run that, what we get is 24. So we've set up our function correctly. We've got the first part to work. Now we can move on to the second. And for that, I'm going to create a little trick. What we want to do next is to add the b squared to the -4ac. Well, we could create one very long equation, but if we do that, we're going to run the risk of getting lost. We won't know which bits refer to which other bits. So what we're going to do is we're going to separate out the different parts. We're going to have this plus, and what do we want to add together? We want to add together b squared. B squared is just times b, and the -4ac. Those are the things that we want to put together. And we can check whether they're together by putting the cursor just after the final bracket. And if the final bracket of that expression covers the whole expression, then we know we've closed the brackets correctly. And we can check whether the whole function has its brackets correct by putting the cursor after that last bracket, that very end one. And if we do that, we can see that the whole definition is highlighted, and because it's highlighted, we know we've got all the bits. Now we can run that with the same function call as before, and what we get is 25. So the next step now is to find the square root of that. So how do we go about doing that? Well, for that, what we're going to do is to add in another line of code. So let's add in square root. So what is it we want to find the square root of? Well, we want to find the square root of the things that we had before. And the things that we had before was this bit. But we need an extra bracket, because if I close that bracket now, you can see it's only defining the square root section, not the function as a whole. So if I add in another bracket, now the whole function is defined. But the indenting is wrong. So what I do is I hold down the control key and hit I. Control and I does the indenting. So now I can see what belongs to the square root, what belongs to the plus, and what each of those parts are. So does this work? Well, let's run it. And yes, we get the answer of 5. So next, what we want to do is to add that to the -b. So how do we do that? Well, quite simply, we put in a spare line again, open the bracket, plus, because that's what we want to add. And then what do we want to add? Well, we want to add what we had before, but we also want to multiply b by -1. That gives us the -b. But if we do that, well, we're a bracket short again. We're a full bracket short of a function. So we need to add that bracket in, and there our function is defined. We can do Control I, and everything is indented. We can see what belongs to the plus. We can see what belongs to the square root. We can see what belongs to the other plus. We're now breaking our function down into its separate bits so that we can read it. And that being able to read something is important because we haven't finished yet. What we want to do now that we've got that plus bit is to divide that by 2a. So we do the same trick again. We add in a spare line, open bracket, and we want divide. And what do we want to divide? Well, we want to divide what we had before, but we want to divide it by 2a, and the bit on the bottom of the fraction has to come last. So what we need now is to know where that plus bit ends. And what we can do is we can keep looking at the brackets until we find the bracket that matches the one that we want. No, that's not it yet. But that bracket, that's the position that says this is the whole of that top line. So into here now, I can add another bit, times 2a. Okay, I've got that. I can put that on its own separate line. And if I do Control I now, well, it indents that nicely too. So let's try running it, and what we get is, oh whoopsie, silly me, I've left out a closing bracket. Well, I'd better put that closing bracket in. Now I've put it in, I can do Control I again. Now I can run it again, and I get the answer 2. Excellent! I've now managed to create a function that finds the first root, but what I'd like is to find both roots. So how do I do that? Well, if you have a problem, cheat intelligently. The difference between the two functions is one is a plus and one has a minus. So that plus in the third line needs to change. I can copy and paste this, and I create now a second function. So this is now going to be R2. And R2 will take obviously the same parameters that I had before, but instead of being a plus, this plus now has to be a minus. And if I put minus in there and run that now, we've got two functions, so we would expect two answers. And yes, it says the two answers are 2 and minus 3. That's good. So we've got the two roots that we're expecting to find for this quadratic equation. Now let's just go back a step, because there's one other bit I'd like to tell you about. As you can see, we've got the two roots that we expected, but, and it's always a big but, we've calculated the roots of 2 and minus 3, but we always have to check. The roots of a quadratic equation should give us 0 if we put these roots into this equation. That's what the roots of an equation are. So let's try that. But what we're going to do is cheat intelligently. It's the intelligently bit that matters. We're going to get Scheme to do the work. And how are we going to do that? Well, we're going to create a function called check. And check works out what you get for a specific value of x in the equation x squared plus x minus 6. And when we do that, we run that function with x equals 2 and then again with x equals minus 3. So let's try that out. Let's go back to Scheme. Here I've defined a function called check that takes one parameter, a value of x. And what I've done is created the formula x squared plus x minus 6. I've broken this down into parts, and again I've used the indenting trick so that I can see where things start and stop. And then I've called that function with 2 and minus 3, the values that we expected to get when we ran R1 and R2. So does this work? Well, yes, we're expecting to get 0, and we got 0 for each one of those. We found the roots of a quadratic equation using a functional programming language, Scheme.